All right, so welcome to lecture 5. So now we're looking into self-adjusting networks, so demand-aware networks that are dynamic. And the goal will be to understand, first of all, binary search trees that are self-adjusting. So we need to remember some of these concepts. And then we build upon it for building self-adjusting networks. And we also discuss desirable properties. And then we learn about one specific self-adjusting network, which is called SplayNet. And we'll study their properties, their algorithms, and finally we conclude by revisiting the ego tree concept and also see how that can be used for building another type of self-adjusting network. All right, so maybe first remember that we had this vision that concepts from data structures and coding can be used also to build self-adjusting networks. And one example here, popular one, or also the first one in the context of binary search trees, was the splay tree. So let's revisit some of the concepts of the splay tree. So the typical model for a self-adjusting binary search tree is that we want to minimize the service cost and the adjustment cost. So again, the service cost is like how much it costs to serve a specific request sigma I on the binary search tree I. And then we pay the price for changing from one binary search tree to another one if we want to adapt it. And mostly here, the serving cost is just the number of links that we traverse for each lookup. And the adjustment cost is the number of links that we want to change from BSDI to BSDI plus 1. And here we assume that the requests arrive online, so we don't know the future requests ahead of time. So what we need to build a self-adjusting binary search tree is that operations that can actually change the binary search tree so that the nodes that are frequently accessed, we can move them closer to the root. And we also need to make sure that these operations always maintain the search property so that we are still able to find the nodes or the items or keys in a greedy manner in the BST. And we always want to keep the other recently accessed items, the recently and frequently accessed nodes, also close to the root. So how to make this requirement formal? So what would that mean here? So there is a concept that is called working set property that has a very attractive characteristics. Is that if you have an access to an item j, let's define tj to be the number of different items that we accessed since we accessed j the last time. So how many different accesses did we have since we accessed j? And actually what we want is that the distance of j to the root is proportional to this amount of different items tj that we accessed since then. So typically here we are interested in the amortized cost or amortized time. So this is like the average cost over a worst case sequence. Okay, so this is like a cost per operation averaged for a worst case sequence. So formally it's the maximum of a sum of the serving costs of these sigma i's divided by the length of the sequence sigma. And this can typically be analyzed with potential functions, so that's a technique, but we're not going into this in this video, but we'll have some of this separately. So for example, for splay trees, it can be shown that the amortized cost of accessing item j is logarithmic in the number of accessed items tj plus 1. So this is quite nice. So the amortized cost is logarithmic in how recently or been accessed there. So this is proportional to the kind of that's what the working set is about, like how many items have been accessed in the meantime. And if it's not many, then this means that we are still close to the root. So splay trees are a particularly interesting type of self-adjusting binary search trees. They have a very simple rule that when you access an item, then you're immediately promoted to become the root of the BST. And this is kind of similar to move to front, which is an algorithm for lists. So it's a very proactive way of optimizing this data structure by just directly moving it up to the root. And for making this possible, binary search trees or splay trees, they have 3 operations. The first one is called zig. So this is like allowing you to rotate parts of the tree to the right. So in this way, for example, here we move x 1 up closer to the root by rotating the subtrees 1 to the right, and this is called like a zig operation. And it preserves also the search property as we wanted. There is also an operation zag that is just for rotating to the left. So rotating to the right and rotating to the left, these are just 2 symmetric ways of doing that. And then there is operation zig-zig. This is like rotating again to the right, but now we rotate it twice. Okay, and then again we move the item x closer to the root, and we still preserve the search property of the BST. And again, there is a symmetric version that is rotating to the left, that is called zag-zag. And then there is operation zigzag, that is first doing a left rotation and then a right rotation. And again, that's how in this picture you can see how this is done. And again, we move x closer to the root, or in this case, it becomes the subtree root. And the search structure again is preserved if you do a zigzag operation like that. And also here, there is a corresponding symmetric operation. This is called zag-zig. So it's doing first a right and then a left rotation. So in order to update the splay tree, again, the idea is to move if you access an item x, or sorry, in this case, if you access an item y, then it's becoming promoted directly to become the root of the BST. And using this zigzag and other operations to move the accessed item y to the root, so the whole sequence is called a splay operation. So if you move an item to the root, we call this a splay. Okay, so this is the promotion that y experiences, and basically splay operation is just a sequence of zig-zag, zigzag, zag-zag, zag-zig operations, and maybe in the end a zig or a zag. So it depends. So the last operation is can be a zig or a zag. All the other operations are zig-zag or zigzag, always 2 operations at once, and just moving this item y to the root. So we only have at most 1 zig or at most 1 zag operation in this splay procedure. It's only the last time, the last operation that we do during the splay is a zig or a zag, depending on whether it's an even or an odd number of times we do this. So what is this working set about? Let's get a bit of intuition here. So let's look at an example. Here we have a tree, and currently 2 is a leaf. And now if we have a sigma access sequence that first accesses the 2, so that means this will be quite costly to access 2. So we have a cost of 4 in this case. But then 2 is promoted to become the root. So the splay operation, if you SplayNet a splay tree, it's moving it directly to the root. And next assume 4 will be accessed. So now the cost of this operation will be 1. So we just have it's a distance 1 from the root. And what the splay tree will do, it will now make a rotation to the left, so that 4 become promoted to be the root. So, but now you can see that actually if 2 is accessed again, 2 is still very close to the root. And that's what the working set property is about, that the distance, if you have been recently accessed and you're accessed again, you still have a very low cost. You're still very close to the root of the BST. So if 2 is accessed now, the cost will be 1, thanks to the working set property. And so what is the amortized cost here? So we have first access cost of 4, then access cost of 1, access cost of 1. So we have 3 operations. So this is 6 divided by 3. So the amortized cost will be, in this case, 2. If you are excited, hopefully, about these splay trees, then have a look also at this online material. For example, there is a nice application of or applet of splay trees in the animation by Daniel Liang. So have a look at that, and you can also play around with accesses and get intuition about the working set using this online material. So one most important lemma about splay trees is called the access lemma. And a lot of the properties that we have is actually based on this access lemma. And it enables a lot of the analysis there. So what we need for this lemma is we define for each node v in the BST, we define a weight wv. And we also define the size of a node v, that is like sv. That is the sum of all the weights in the subtree of this node v. And then we also define a rank, which is the logarithm of the size. So the rank of v is just the logarithm of s of v. So what the access lemma states is that the amortized time or the amortized cost to splay a tree with a root u to a node v, okay, so the cost of splaying then v to the root is 3 times the rank of u minus the rank of v plus 1. And actually you can show that this is in the order of the logarithm of the size of u divided by the size of v. So this is what the access lemma states. And when you have this property, what you can do is you can, for different, if you have this access lemma, you can think about different weights to set in the binary search tree, so that you can use the access lemma to, for example, prove the working set property. You can also prove static optimality, so splay trees that you can show that the splay trees are never worse than the optimal static tree. So remember from the earlier lecture that the static optimality always compares an online algorithm to a static optimal solution. So we can actually show that the splay trees are statically optimal. Actually, we still don't know about dynamic optimality for the splay tree. So this is one of the very interesting open questions in theoretical computer science. Okay, so that was about self-adjusting binary search trees. So, but of course, we are very much interested in networks in this course. So what is the difference here? So in a data structure, requests always come from a root. And then like in a binary search tree or also in a Huffman tree, we have this access from the root. In a network, routing happens between any pairs of nodes, right? So that's a difference here. And also we have this cost model in the network context that we have, like on the one hand serving costs and adjustment costs. So for example, route length plus the number of links that we change. So here an illustration. So according to the concepts of splay trees, we can also define a concept of SplayNets. So this is like a network version of the splay tree, where requests are now not coming from the root, but request sigma I is between a source and a destination. And the nice property of splay trees is that you can do local search, right? You can do greedy search on a binary search tree. That if you know for a node V, if you want to find the key, then you can just check, is the key smaller than V, then you go to the left, or is the key larger than V, then you go to the right. And it would be really nice if you could also have such a routing, greedy routing property in a network. Okay, so how can we do something similar in a network? So now, unlike in a data structure, we're not coming only from the root, but we are also having like a source that may be anywhere in this network, right? So how can we do a greedy routing from S to D, from source to destination? And if you have a binary search tree, we can actually still have this local greedy routing. And it works like this, that now for each node U, you need to consider the subtree TU, rooted at U. And you need to remember U prime and U prime prime, which is like the smallest and the largest value that are in this subtree TU. And now, if you want to route from source to destination, again, we may also have to go up. So far in data structure, we only had to go down, but now we also have to go up. And we basically can do the following local greedy forwarding. If the destination is somewhere between U prime and U, then we need to forward it to the left, okay? And if the destination is somewhere between the U and U prime prime, then we have to forward to the right. And everything else, we forward it upwards. So now we have this new dimension that we also have to move upwards. And that's how we can actually get greedy routing also in the context of a network where we have arbitrary pairs. And this is quite attractive in dynamic networks to have such a local greedy routing, because basically we don't need to recompute routes if the topology changes. So the control plane doesn't have to reconverge. We don't have to recompute shortest paths or anything like that, because we have this local rule. So how can we now adjust a network that is like inspired by these splay trees, but that we have these pairs of communication sources and destinations? In the splay tree, remember we had this access from the root, and then if y was accessed, it was promoted or splayed up to become the new root. In a network, we have this S and D, and what we could do is we could just upon access, or if S accesses D, we could, for example, move both of them individually to become the root of the binary search tree. So we could splay them up, both of them, to become the root. But that may be quite inefficient, because we have to promote them all the way up to the root. So what would be nice to have is that we only look at this subtree in which the both source and destinations are included. So we can define this least common ancestor. So this is the root of the subtree where both S and D are in. And then we can do a splay of the source to the LCA of the least common ancestor. And then once S has become the root of this tree, we could also splay up the destination to become the child of this source. So that will be making the two neighboring. So we can make them directly become neighbors, like in the splay tree where they become the root, the access data become the root. In the SplayNet, the source and destination can become neighbors in the least common ancestor, or in the subtree where they are located. So concretely, if you have this S and D request, then we promote S to become the root with a splay operation. And then we splay D also up to become the child of the S, of the source. And this operation that includes two splay operations, we call it a double splay operation. So we are kind of combining the two. And to give a more concrete example, if you have this SplayNet here, this binary search tree where we have arbitrary pairs of requests, if 14 communicates to 9, we look at the subtree in which they are in, and then the least common ancestor in this case is 12. So what we do, we splay 14 up to 12. So we do the zigzag operations that 14 become there. And then we splay 9 to become the child of 14. And then this is like the new SplayNet tree that we get. And also here, there is online applets that you can play around to see a bit what's the behavior of these SplayNets if you have different accesses. So please have a look there. I think it's quite nice to see also the different properties. All right, so what's the performance of such a SplayNet? And I just want to give you two bounds for the SplayNets. The first is the upper bound, so the cost or the amortized cost of the accesses or the routing requests. And we can show that asymptotically the cost of a SplayNet for a given sequence sigma is just the entropy of the x plus the entropy of y. So and here x and y are just the frequency distribution or the frequency probability distribution for the sources x and for the destinations y. So this is very similar to in splay tree where the access cost is related to the entropy. Now in the SplayNet, basically the access cost is the entropy of the sources plus the entropy of the destinations. And what is the idea of the proof here? So let's consider any node V. And we can define SV now to be the number of times V appears as a source in sigma. And similarly, we can define d of V as the number of times it's a destination. And then for each node V, we can assign a weight that is like the S of V divided by M or the d of V divided by M. And then we can analyze the basic operations of SplayNets separately. So we have first a splay operation to the source. So basically we splay the source to the least common ancestor. And then we have a second splay operation where we do the destination splay to become the child of the source. And that means that the cost of the SplayNet is given by this splay operation of the source plus the splay operation by the destination. And we need to divide this by m. Which is the length of the sequence. So that's the amortized cost of the SplayNet for a given sigma. And since the size of the source is at least SV divided by M, and the size of any node is at least 1, so we cannot have a size smaller than 1, and actually the same for destinations, we can use the access lemma to show that the upper bound is indeed this asymptotically the entropy of the sources plus the entropy of the destinations. So that's a nice upper bound. It connects back to this matrix that we saw in binary search trees. Also can be used in this context of networks. And again, we know exactly from that literature that the cost of splaying the source is the entropy of the x, and the cost of splaying the destinations is on the entropy of y. So how good is that bound? We can also show that the cost is at least the conditional entropy. So given the destinations what's the entropy of the sources given the destinations plus the other way around. So that will be a lower bound for the cost of the SplayNet. And in order to see that, we can see that for any node x, we can define a variable, a random variable y x, that is like the frequency distribution or the probability distribution of the destinations given the source is x. So we can define this conditional variable. And then we can consider an optimal tree t with this root x. And we know that, again, from the literature of biased binary search trees, that the average path length of requests is in the order at least of the entropy of this variable y given x. Okay, so this is just a classic binary search tree. And then if you consider this optimal tree for each source, we have a cost now that is at least, and now we can compute this together, is the sum of the frequencies of this x times basically the entropy of this random variable y given x. And that again is just basically asymptotically, this is just the entropy of y given x. So what we can show here is that the conditional entropy is a lower bound for this cost of a self-adjusting binary search tree. And yeah, so this I showed you for the sources, but you can show something similar for the destinations. Okay, so how good is this now, or when are how far away are these upper and these lower bounds? And you can see by these two lemmas that we showed that sometimes SplayNets are actually optimal self-adjusting binary search trees or binary search networks. Because if you, for example, consider product distribution, that is one example where binary search trees or these SplayNets are optimal. So what is a product distribution? This is like a very important special distribution where the property holds that if you look at the probability p of u and v of a communication request uv, you can basically describe this joint probability by the multiplication of the activity or probabilities pu and pv separately. So if for a joint distribution puv, this is just the probability of u times the probability of v, this is called a product distribution. And in this case, if you have a product distribution, if the demand is kind of a product distribution or is sampled accordingly, then you can show that SplayNet is actually optimal. And this directly follows from this lemma 1 and 2, because from the independence, you know that the conditional entropy of x given y is actually just the entropy of x and the other way around. So the conditional entropy of y given x is just the entropy of y because we have the independence. So this way you can see that the upper and the lower bound match, and for a product distribution the SplayNet is actually optimal. All right, so that's one way to do self-adjusting networks by having these SplayNet that are just a generalization of splay trees. There is also an alternative way to go about designing dynamic demand-aware networks. And for this, we can just go back to this idea of an ego tree that we use to build static demand-aware networks. And if you remember from the S10 problem that we had, we built basically ego tree for each of the rows, for each of the sources, and then we take the union, and then we reduce the degree. So that was our approach there. If you want to make a dynamic demand-aware network, one nice idea that you could have is you could simply make these binary search trees or these ego trees not static, but you could make them dynamic. So if each of these ego trees would, for example, be a splay tree or would be a Huffman tree, then you do the same tricks of union, making the union of them and then reducing the degree. You basically get a nice self-adjusting network as well. And you can actually show some nice properties of those networks. So besides splay trees, there are also other types of trees you can use. For example, Huffman trees and pushdown trees, etc. All right, so that concludes our look a first look into dynamic demand-aware networks. So we've seen how actually classic concepts from splay trees can be used here. We also saw some model and properties that we would like to have in self-adjusting networks. And we presented in more detail one example that is called a SplayNet. But in the end, we also saw there are other ways to do self-adjusting networks. So that concludes this lecture. And in the next lecture, we'll see how some of these concepts apply in the context of data centers. Thank you.